Up until this point, working with series, we have been focusing on ordinary points and kind of avoiding the case of singular points. And so that's what this video is going to take a look at. The question, how do we create series solutions about singular points? If you recall, those singular points were those points where the equations P and Q are not analytic. In other words, we can't make a power series to represent those coefficients. And so we need a different method in order to find a series solution for the differential equation. And one such method is called the Frobenius method. And the idea of the Frobenius method is if x equals 0 is a singular point, then the expression or equation y equals the sum as n goes from 0 to infinity of c sub n x to the n plus r provides at least one solution. And in fact, it provides two solutions if our options for r, we're going to have two options for r, r1 and r2, don't differ by an integer. If they do differ by an integer, they may or may not provide two independent solutions. So the big idea here is what we're saying is if y is equal to the sum as n goes from 0 to infinity of c sub n times x to the n plus some r, then our y prime would be equal to the sum as n goes from 0 to infinity of n plus r times c sub n x to the n plus r minus 1. And y prime prime would be the sum as n goes from 0 to infinity of n plus r minus 1 times n plus r times c sub n x to the n plus r minus 2. And for higher derivatives, we could go even further. What we notice here, first off, that's different than what we saw before with power series, is because we have an exponent of n plus r, when that comes out front, n plus r does not end up multiplying by 0. So the n equals 0 term does not go away when we take derivatives. All of these series with the Frobenius method are going to start at n equals 0, at least initially. We're going to do some work on them as we go on. That might change the index, but at least initially, we always start at 0. So with these substitutions for y, y prime, and y double prime, let's work on solving an example. Let's solve the equation of 3x y double prime plus y prime minus y equals 0. Well, substituting using the equations up above, we'll end up with the sum as n goes from 0 to infinity of, because we have a y prime, 3 times n plus r minus 1 times n plus r times c sub n x to the n plus r minus 2 plus 1 is just going to be a minus 1 because we're multiplying by that extra x, plus y prime is the sum as n goes from 0 to infinity of n plus r c sub n x to the n plus r minus 1, plus, or minus, actually I'm going to put that minus into the sum. The sum as n goes from 0 to infinity of negative c sub n x to the n plus r, and all of that is equal to 0. This is what we're going to want to solve to find our series solution. Something that we're going to do different with these is we are going to try and get all the exponents on x to match, which means this last term is missing the minus 1. So if I want to make it an n minus 1 and subtract 1 from the n's, we know that means we have to add 1 to the index. So what that's going to do is create the sum as n goes from 0 to infinity of 3 times n plus r minus 1 times n plus r c sub n x to the n plus r minus 1 plus the sum as n goes from 0 to infinity of n plus r c sub n x to the n plus r minus 1 plus the sum as n goes from, now it's 1 to infinity, of negative c sub n minus 1 x to the n plus r minus 1 equals 0. And this is nice because now we have created a situation where we have all the exponents matching as n plus r minus 1. That's the first thing we want. The second thing we want, though, is all the indexes to match. I heard the example that if you think about this as 3 individual factories that are going to run, the first few factories are opening at midnight, or n equals 0. So they're going to run for 1 hour, while the other factory that starts at 1 a.m. is going to just hang out and do nothing until 1 o'clock when it starts running. So during that 0 hour, we're going to run the first term. So let's plug 0 in for n. When we plug 0 in for n, pulling out the first term from both of those, we get 3 times 0 plus r minus 1 times 0 plus r c sub 0 x to the r minus 1 plus, plugging 0 in, we've got 0 plus r is r, c sub 0 x to the r minus 1 plus, and now we have all these indexes that match going from n equals 1 to 0. They also all have an x to the n plus r minus 1 because we made that match on the prior step. And then that leaves behind 3 times n plus r minus 1 times n plus r c sub n plus n plus r c sub n minus c sub n minus 1 equals 0. All right, now we're ready to start solving for our coefficients, just like we did back with power series. Something special, though, is going to happen with the x to the r minus 1 powers. If I factor out x to the r minus 1 and a c sub 0, what's left is 3 times r minus 1 times r plus r. That all has to equal 0, which means, because c sub 0 can be anything, not necessarily 0, x to the r minus 1 can be anything, not necessarily 0. What we can control is the r's. And if I distribute, we've got 3r squared minus 3r plus r is 2r equals 0. Factor out an r, leaving behind 3r minus 2 equals 0. I have 2 options for r. R equals 0 or 2/3. That's going to help me reduce from having variables in r and c sub n. Now we're going to use these r values to replace those, but not quite yet. I'm going to pause for a minute for a little bit of vocabulary. This equation that we end up with pretty much is going to have an r minus 1 times r plus something times r plus a constant. That thing, that piece, we often call the indicial equation. That's going to tell us what the r's are equal to. So if you come across that phrase, the indicial equation, it's talking about that piece that we pulled off to solve for our r's. All right, back to the other side, the sum. We know with the sum, this whole bit in the parentheses needs to also equal 0. I'm going to factor out c sub n from the first 2 terms as I do that. So we'll have c sub n times 3 times n plus r minus 1 times n plus r plus an n plus r. And then there's a minus c sub n minus 1. We know that must equal 0. See, in my next step, I'm going to factor out the n plus r. That'll leave behind a 1. I'm also going to distribute the 3 through while I do that. So doing a couple things at once. We factored out the n plus r. We distribute the 3 through to get 3n plus 3r minus 3 plus 1 from the other one that got factored out is minus 2 times c sub n minus c sub n minus 1 equals 0. We always solve for the larger subscript. So in this case, it's going to be the c sub n. We can solve for that by adding c sub n minus 1 to both sides, and then dividing by the n plus r times 3n plus 3r minus 2. And now we've got a function that relates each term to the term before it. But we also have 2 values for r that we're going to use to help us simplify this. So we're going to consider 2 cases. Case 1, always start with the larger one, r equals 2/3. Turns out if your numbers differ by an integer, these ones don't, but if the numbers differ by an integer, the larger one tends to give you the case that you're looking for. The smaller one we'll only look at if we differ by an integer, don't differ by an integer. In this case, we do not, so we will look at both cases. And then we're going to use different letters because I don't want to get the c sub n confused with the 2 cases. So I'm going to call this a sub n, because this is my first case, is equal to a sub n minus 1 over n plus 2/3. Remember, we said the r was 2/3, times 3n plus 3 times 2/3 is 2, minus 2 is 0. And what's nice there is I can distribute the 3 through, not the n, just the 3 through, to get rid of the fraction in there. And so we have a sub n minus 1 over 3n plus 2 times n. And now we can run through our cases to try and find our pattern. Just like we did with power series, we said this series was going to start at n equals 1. So if n is 1, a sub 1 is equal to the previous term, a sub 0, over 3n plus 2 is 5, times n, which is 1. When n equals 2, a sub 2 is equal to, and I always kind of treat the a sub n minus 1 separately, so I have 1 over, plugging 2 in, 6 plus 2 is 8, times n, which is 2, times the previous term, which is a sub 0 over 5 times 1. If n equals 3, plugging 3 in, we've got 1 over, 3 times 3 is 9, plus 2 is 11, times n, which is 3, times the previous term, which is a sub 0 over, and I'm going to group the 8 times 5 together and the 2 times 1 together. And you kind of start to see a pattern. We end up with a sub 0 over. We've got 11 times 8 times 5. We've also got a 3 times 2 times 1. Kind of comes in 2 groups. Similarly, up above it, we've got the a sub 0 over. We've got an 8 times 5 and a 2 times 1. And finally, in the a sub 1, we've got the a sub 0 over just the 5 and just the 1. So if we're looking to express the a sub n term, clearly we have an a sub 0. And then we've got this 11 times 8 times 5. That's adding 3 every time. We don't really have a notation to say add 3 every time, so we're going to just write down the pattern that's established. It's 5 times 8 times 11, increasing by 3, ... Because we're increasing by 3, it's 3n. And then we have to kind of decide where it's going to stop. When when n was 3, 3 times 3 was 9. 9 plus 2 stopped at 11. So when n was 3, we stopped at 11. So that looks like the formula there. And the second half is obviously just going to be our n factorial. So if we put that all together, we get our first set of independent solutions. We're going to have an a sub 0 times, now I've got to be careful here, the pattern here is starting at 1. If I were to plug 0 into this formula, the 3n plus 2 would say to multiply by a 2, and there is no multiplying by 2 actually happening. So the series, the pattern actually starts when n equals 1. So we have to account for when n equals 0 kind of independently. So we're just going to put a 1, because a times 0 times 1 gives us that a sub 0 term that's not accounted for in the pattern, plus the sum as n goes from 1 to infinity of, and remember with the Frobenius method, we use x to the n plus r, in this case r was 2/3, divided by that pattern we established in the denominator, 5 times 8 times 11 times, all the way up to 3n plus 2 times n factorial. And that is our first case when r equals 2/3. However, there was a second case that we also had, case 2. We said r could also equal 0. I copied the formula here. If I were to plug 0 into that formula, this time we're going to use b as our subscript, so we know it's different than the a sub 0. b sub n is equal to b sub n minus 1 over n plus r is just n times 3n plus 3r is 0 minus 2. And now we can run through the series again and find the pattern for this second coefficient. We said the series was going to start when n equals 1. That gives us b sub 1 is equal to b sub 0 over 1 times 3 times n minus 2 is going to give us just 1, 3 minus 2. When n equals 2, b sub 2 is equal to the previous term, and I'm going to treat that previous term in a second fraction. So we'll do 1 over, n is 2, times, plug in 2n, 3 times 2 is 6, minus 2 is 4, times the previous term, which is b sub 0 over 1 times 1. When n equals 3, we have b sub 3 is equal to 1 over 3 times 9 minus 2 is 7, times the previous term, which is b sub 0 times a 2 times 1 and a 4 times 1. And again, we're noticing this time it turns out we get a really similar pattern. At the first, the n is becoming a 3 times 2 times 1, and the 3n minus 2 becomes a 7 times 4 times 1. And you can see that pattern as we go up with a 2 times 1 above it and a 4 times 1. And above that's just the b sub 0 over the 1 times the 4. So when we're trying to generate our b sub n formula, the numerator is b sub 0. The first set of factors is obviously an n factorial. The second set of factors is, again, that increasing by 3 thing. So we'll establish the pattern. We don't really need to write the multiply by 1. So I'll say 4 times 7. I'll do one more. We know the next one's going to be 11. Times, times, times. And because we're increasing by 3, we know it's 3n plus or minus something. So we'll test it that the third term should stop at 7. 3 times 3 is 9, so I need to subtract 2 to get down to 7. And just like last time, we can put that together to get our second linearly independent solution for y, this time with b sub 0 factored out of everything. Again, for the same reasons, we are going to start at n equals 1. The pattern does not hold at n equals 0, so we'll do a 1 times b sub 0 gives us the b sub 0, plus the sum as n goes from 1 to infinity of, and in the numerator we've got x to the n plus our r. That's what makes it the Frobenius method. R this time just happens to be 0, so n plus 0, over our pattern of n factorial times 4 times 7 times 11 times 3n minus 2. And that gives us our second linearly independent solution. Of course, we know we can put those both together. We know y is equal to our a naught times the first solution plus the b naught times the second solution. So we can write this out by combining the two answers that we got above. Y is equal to a naught times 1 plus the sum as n goes from 1 to infinity of x to the n plus 2/3 over 5 times 8 times 11 times up to 3n plus 2 times n factorial plus b naught times 1 plus the sum as n goes from 1 to infinity of x to the n plus 0, or just n, over n factorial times 4 times 7 times 11 times, all the way up to 3n minus 2. And this then becomes the general solution as a series, an infinite series, for our differential equation. And because we use the Frobenius method, we know both series will converge to our solution. All right, the process is really similar to what we saw with power series. The only real difference is we're going to do that x to the n plus r, which changes the derivative slightly and gives you that indicial equation to solve for your two options for r. Practice these, get really good at them, and we'll see you in the next video.